Hi everyone, today we're going to start on our next topic, which is 3.5, basis and coordinates. So we actually learned about basis and coordinates last year in chapter 1 in multivariable calculus. So the concept actually is not different, it's exactly the same. The only difference is that what we're going to try to do now is try to apply the concept of basis and coordinates on other vector spaces, and you actually see me try to do that a few times already in other in section 1 to section 3.1 and to 3.4 already. So it's not actually technically new, but we're just now ready to formally recall, formally define how that works. So recall from last year in BC calculus, in multivariable calculus. If you have given a position vector, vector x, can a position vector can always be represented as a linear combination of a given set of vectors, which gonna call them vector u1, u2, dot 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 to un, with a set of scalars, which I'm going to call them a1, a2, dot 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 to an, as their coefficients. So therefore, meaning that vector x is actually equal to a1 vector u1 plus a2 vector u2 plus dot 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 plus an vector un. In this expression right here, the set of vectors, which are u1, u2, dot 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 to un, this set of vectors is called a basis. And the scalar, actually maybe I'll write it this way, the set of scalars collectively are called coordinates. And they form a coordinate vector, which is a1, a2, dot 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 an in Rn also. So the general idea here is that you're basically changing the position vector into a coordinate vector of the same dimension. Okay, if you are basically talking about position vector in Rn, then it will require n that many vector in the basis. Now, we talked about all this last year, but we didn't really define a lot of the things that we used last year. As a matter of fact, some of the word that you probably hear me use a lot last year, but we actually don't have a formal definition of it, would be dimension, which intuitively most of you understand what that means, but we haven't really give our definition for it, and which we're going to do this year. So now what we're going to try to do is basically try to do the same thing. The only difference is we're going to try to define it in more general term, not as vectors in Rn, but hopefully apply the same concept to matrix space, polynomial space, continuous function space, continuous first derivative function space, and so on and so forth. All right, so we talk about this in 3.2. If we're given a vector space, so this vector space could be Rn, just like what you're thinking, but it could be any other vector space, V. Let S be a subset of V. Then based on what you learned in 3.2, then the span of S will form a subspace of V. So now what we basically try to do is try to use span to describe a vector space. Now, if the span of S is the entire vector space V, then S is called a spanning set of V. Now notice the terminology being used here is called spanning set, but not a basis. Why? Well, because there's a difference between a spanning set and a basis. That's the reason why it's not called basis. If S is linear independent, then S form a basis for V. So the key difference is these concept right here, linear independent. So what is the reason, or what's the significance of the fact that S has to be linear independent for it to form a basis for V? The reason why, because if you have a set of S that's linear independent and yet can be the spanning set for the entire V, you basically, what you find is the fewest number of elements you need to span the entire set of V. So in another word, for instance, based on what you have learned from last year, you realize that for R3, we have a basis called a standard basis, which use 3 vectors to span the entire R3. The idea here is that a spanning set could have 3 vectors, or 4, or 5, or 6, or 7, or more vectors for R3. But if you want them to be linear independent and also be able to span the entire R3, you must have 3 elements. That's what the linear independence do. It reduces the number of vectors you need in the spanning set down to its bare minimum that needed to span the entire set V. So as I said, for R3, you could have a lot of spanning set, and some of those spanning set can have 4, 5, 6, 7, or more elements in it. But to form a basis for R3, you have to have 3 elements. 3 linearly independent elements. Now, why is that significant? Because of the following. Okay. Is this concept right here. So this definition right here, if S is linearly independent and it spans the entire set, that's what it forms a basis. So that's the kind of the definition of what a basis is. So I guess I can write out the definition. So here's the definition, which is 3.5.1, which states the following. A basis for a vector space V is a set of vectors in V that is both linear independent and span entire V. So both of them has to be important. So have to be linear independent and have to span the entire V for it to form a basis. Now, why is that significant? Because, as I say, the linear independent kind of guarantee that your spanning set would be the smallest possible. So because of that, we can now actually use that basis to actually define something else, which is something that we've been using a lot, but we haven't have a formal definition of that. If V has a finite basis, let's say the basis is B1, B2, to Bn, consisting of n vectors. Now, important is that I define it to be a basis. So therefore, we're implying that B1, B2 to Bn would span the entire V, and they're also linear independent of each other. So if that's the case, then we go define something called dimension. Then V has basically what we call dimension n, written as this: DIM parentheses V is equal to n. So therefore, we're defining the dimension of a vector space by using the number of elements in the basis, not in the spanning set, because spanning set could have more than needed to span the entire space. But in a basis, because they have to be linear independent, they only form the smallest number needed to span the entire space. And that allows us to define n to be the dimension. Now, there are two types of vector space that are unique, so I want to point them out. Okay. Number one, note the following. If V consists of only one element, and that one element has to be the zero vector, because otherwise it would not be a vector space. If V consists of only one element, the vector 0, then we can say that the dimension of V is 0. So that would be a 0 dimension. So the 0 subspace actually have 0 dimension because there's only one element in it. As soon as you move beyond dimension 0 to dimension 1, you have infinite number of elements there, because without infinite number of elements, it would not satisfy the closure properties. Now, what if you have a vector space that doesn't have a basis? So if V does not have a finite basis, implying that V is not spanned by a finite set of vectors, which could mean that, most likely mean that V is spanned by infinite set of vectors. Then V is referred to as an infinite dimensional. So if it doesn't have a finite basis, then we'll have to refer to it as an infinite dimensional. Whether it's because it doesn't have a basis or its basis actually is infinitely large. Now, give you a very simple example to talk about basis and dimension. Imagine the following. Consider the vector space Rn. Its standard basis, which we already know, will contain n vectors in it. Therefore, its dimension would be n. So if you recall, for example, in R2, the standard basis for R2 would be E1 and E2, or 1, 0 and 0, 1. And so therefore the dimension of R2, shockingly, is 2. Similarly, in R3, the standard basis would be E1, E2, and E3. Oops. Or 1, 0, 0, 0, 1, 0, and then 0, 0, 1. So therefore the dimension of R3 would be 3. So on and so forth. Okay, so this continue on to Rn. And it shouldn't be too hard for you to think about and understand that 1, 0, and 0, 1 will allow you to define the entire xy plane, because any single point on the xy plane can now be determined by 2 separate coordinates. Okay? Now, so that's not very exciting, because you kind of already know that. So how about we look at a different example, because Rn is probably the first vector that you kind of learned last year, and we actually, as I say, we talk about the standard basis for it in chapter 1 last year. So that's not exciting. So how about we talk about this vector space, a different vector space. Let's consider Pn, the polynomial space. But notice they have the n subscript, so therefore it has a polynomial space of all polynomials of n degrees or less, so meaning in the form of p of x is equal to a sub 0 plus a1x plus a2x squared plus dot 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 plus an x to the n. So it shouldn't be too hard for you to figure out that P sub n has a spanning set that allow me to span the entire polynomial, because if you simply just look at P of x, you see that P of x actually is a linear combination. And the coefficients are collected to be a sub 0 to a sub n. And that leaves the rest of the expression to be the basis. So in this case, you can see that P sub n has a spanning set of 1x x squared dot 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 to x to the n. And because you cannot add any two of these together to form any other one, they are definitely independent, because they all, in this case, the easiest way to identify that they are linear independent is that because they're all unlike terms. So there's no way for you to combine them together or in some way form one of the things in this list by adding any two or more of other things together. Now, we will talk a little bit more about how to define linear independent later on, okay? So therefore, we will have a more formal definition and formal method to define this. But this should be clear to you that none of these can be combined to form any other one. Because remember, when you talk about linear independence, you talk about linear combination. So there's no way for you to add any two of these elements to form a third one within the set. So if you count correctly, there are actually n plus 1. Since they are linearly independent, this set form a basis for P sub n. Therefore, the dimension of P sub n is actually equal to n plus 1, because we start with the number 1 and then go up to, which is x to 0 power. So if you go from 0 to n, you actually have n plus 1 that many elements. Okay, now because of the fact that P sub n has a finite number of elements, therefore it will have a dimension. Now, however, on the other hand, P has a basis 1 x squared forever. So therefore, in this case, P is, technically speaking, infinite dimensional. Because the spanning set actually has infinite number of elements in it. So slightly different. So in this case of P, without the subscript, you talk about polynomial function in this form. It doesn't have a highest power term because the term keep going forever. And because of that, it becomes infinite dimensional. Good. Now come a very important theorems. The idea here is that when you have a basis properly defined for a vector space, it now allows you to actually talk about using the coordinates as a way to describe any elements within the set. And because of that, that would mean that we now actually be able to, instead of talking about a vector space of some weird, unusual objects, we can now focus on just the coordinates of the vector space, which would actually form a vectors in Rn, and therefore become something that we can actually use and do math with. So that's basically what we work toward, meaning that even if you have a continuous function subspace, where it's defined by actually having functions, but if we can somehow define a basis for that subspace, we can then just talk about vectors in Rn, numbers. So that's very powerful. So show you, this is the theorem that I want to show you. 3.5.3, which states the following. Let's say let B, which is equal to B1, B2, to Bn, be a basis for a vector space V. Then, for every vector V in V, there are a set of unique actually I should write it this way. I put the word unique in the wrong spot. There are actually maybe I should say there is a unique set of scalars v1, v2, to vn, such that vector v is equal to v1, b1 plus v2, b2 plus plus vn, bn. And this correspondence between the vector v and the set of scalars, this correspondence this correspondence is a linear correspondence. So therefore, we can actually have a way to change a vector in a vector space into a list of scalars. And of course, in here, the key takeaway is that this list of scalar v1, v2, to vn, they together form the coordinate vectors. v1, v2, to vn. And the important part is that this correspondence is linear. Therefore, meaning that imagine that you basically plug the vector v into this linear operator, and then it outpop a vector in Rn. So in a sense, this basically this linear operator basically take a vector v in v and transform it into a coordinate vector in Rn. That's basically the important part of this theorem. Now show you how this works, or show you why this correspondence is linear in a sense. Okay? So show you why this correspondence is linear, and that will probably be the last thing I'm going to show you today. So imagine the following. Okay, let's say we're going to have two vectors. I'm going to have vector x and vector y in v with, let's say, bases. I kind of want to use a and b for the coordinates, and I already use v for like element within v. So here maybe I'll change it a little bit. Yeah, let me do this instead. So let's say I'm going to say with basis u1, u2, to un. So here's my, so vector v is n-dimensional, and it has a basis of u1, u2 to un. And let's say x and y are both in v. So therefore, what I want to show is the following. We know that for every element in V, there is a unique coordinate vector that defines that element with the corresponding basis, implying the following. If I have vector x, I can rewrite vector x as a1 u1 plus a2 u2 plus plus a and un. Therefore, implying that vector x, whatever this vector x is, can be changed into, actually maybe I'll write it this way, can be changed into a coordinate vector a1, a2 to an. Okay, so that is the coordinate vector for vector x. Vector could be anything, could be a different object, but now I have a vector in Rn that represents its coordinates. And let's say we have y, which will be b1, u1 plus b2 u2 plus plus b and un. So therefore indicate that b1, b2, to bn is basically the coordinate vector for y. Now what I want to show is the following. If I have a linear combination of x and y, would that simply just mean linear combination of their coordinate vector? Okay, so therefore here's the question that I want to figure out. If I do s vector x plus plus t vector y, would that simply transform into s times the coordinate vector plus t times the coordinate vector for y? Is that going to be true? So that's what we try to figure it out. All right. So how? Well, I see no reason why we cannot just go for it and see what happens. So let's say I have s times vector x plus t times vector y. Now, knowing that vector x actually can be written into a linear combination, I'm just going to expand it. And then I'm going to do the same thing for y. And now since I have a scalar multiplied to a linear combination, I can simply distribute the scalar. So therefore what I'm going to do is I'm going to say, well, that would just be SA1 vector U1 plus SA2 vector U2 plus dot 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 plus SAN vector UN plus TB1 vector U1 plus TB2 vector U2 plus dot 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 plus TBN vector UN. And now what I'm going to do is the following. Since now this basically have n, two n that many things I'm adding up together, but they actually pay up because of the vectors involved, I can now group them together and pull out the common factor and say, oh, that's just the same thing as SA1 plus TB1 of vector U1 plus SA2 plus TB2 vector U2 plus dot 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 plus SAN plus TBN of vector UN. And therefore, now I just represent the sum or linear combination of vector x and y into a coordinate vector with the bases u1, u2 to un. So therefore, this just become the coordinate vector SA1 plus TB1, SA2 plus TB2. And hopefully by now you see where we're going with this. And then to SAN plus TBN. So that becomes the coordinate vector for this linear combination. And it shouldn't be too hard for you to see that that would just simply mean I can separate into two vectors. And then I can pull out the common factor. And voila. It showed that if I have a linear combination of the vector x and y, it's nothing more than just the linear combination of the coordinate vector. And that showed that the correspondence between them is linear. Now, unfortunately, I'm going to have to stop right here. So I would want to show you an example, but I just don't think I have time for this video because it's already 33 minutes. So we'll continue some more in tomorrow's video. All right, talk to you guys later. Bye-bye.